it is there in your this one, no? Google Classroom. You can check it. Assignment number 3, and due date is today. Okay, so you just can go to the link of assignment 3, and there you can submit. There you can submit your assignments. Okay. Okay, now your next topic. So this is your index compression. Okay, index compression. So last class what we have done was index construction. Today we will see index compression. So index compression is normally done in order to employ a number of compression techniques. Okay, so in order to employ a number of compression techniques for the dictionary and the inverted index that are essential for efficient IR system. So sometimes your number of terms may be very large, and this may lead to your this one retrieval system inefficient. Okay, sometimes your IR system may fail to perform the certain retrieval techniques. So in order to provide an efficient IR retrieval system, we are employing a number of compression techniques. Okay, so this compression techniques will be used in order to compress the size of the the size of the terms, number of terms, or the dictionary size, or also we call it vocabulary size. So this process is known as index compression, and by performing the index compression we need a less disk space. So what are the benefits you have? You can see here. It increased use of caching. It can feed a lot more information into main memory. That means we can put a lot of memory into the. Oh, sorry, we can feed a lot of information into the main memory, accessing its posting list in memory and decompress it. Then after that, what you have to do? The compress. Your compressed number of terms or compressed dictionary, it will be loaded into the memory, and finally if we want to access it we have to access the posting list in the memory itself. After accessing the memory in the after accessing the posting list in the memory, we can finally decompress it. So this is one benefit for index compression. Other benefit is, since the size becomes smaller than the original size, it will help in faster transmission of the data. That means the transfer of data from disk to memory will be faster. So these are the advantages of index compression. Okay, now we have two types of compression in general. So in general, we know we have two types of compression. One is lossless compression, then the other one is lossy compression. So lossless compression is nothing but all the information will be preserved, restores and rebuild the data in its original form after decompression. So with lossless, here itself we can see that there won't be any loss of data. So compression technique will be applied to the information Even after applying the compression technique to the information, when we get back the data, when we restore the data, we will get the original form of the data after decompression, that is lossless compression. And in lossy compression, so it discards or it removes some information, and also it does not restore the data in its original form after decompression. Okay, so after decompression, you might lose some data. So in lossless compression, no all information will be there, no loss of data after decompression. Whereas in lossy compression, it can remove or it can discard some information. That means it does not restore the data in its original form after decompression. So we have before coming to the compression techniques, first we will be learning how to estimate the number of terms using Hip's law. Using Hip's law, estimating the number of terms. So estimating the number of terms here, it will estimate the vocabulary size as a function of collection size. So we will be using this formula to estimate the number of terms, and where T is the number of tokens in the collection and K and B are some parameters which values are ranging from 30 to 100 for K, and B we normally use 0.5. The original value is 4.9, but in our calculation we will round up this 4.9 into 0.5. Okay, so that's why directly I'm writing here 0.5. The original value for B parameter will be approximate value is 0.49. So when we round up, we will be using as 0.5 in our calculation. And K, the value ranges from 30 to 100. And for K, normally for an efficient retrieval system, we will be using K equal to 44. So K equal to K equal to 44, it gives an efficient retrieval result. So we will be using for 44 for K. The fit is excellent. So here also you can see here the fit is excellent for term greater than 10 to the power 5 for parameter value 0.49 and K equal to 44. So 0.5 also you can use here for, because 0.5 and 0.49 almost you will get the exact value. So here similar value, the approximate value of for 0.5 so you can use 0.49 or 0.5, and K equal to 44, if we use, the fit will be excellent. So the parameter value for K will be 44, and for B you can use 4.9 or 0.5. It will give you the similar results. So now we will see how to calculate this one. For example, if there are this number of terms or tokens, they are similar, okay? So we have seen this in inverted index. In our second topic, we have seen about these tokens. So tokens are nothing but the dictionary terms. So each individual terms we will be considering as tokens. So that this is tokens, and Hip's law predict C number of terms. C number of terms. So this is already for Hip's law calculation. Calculation results 38,332 terms. When when there is 1 lakh, 10 lakhs and 20 tokens. 10 lakhs and 20 tokens. So we got this value. How? So by using the formula m equal to, m is nothing but the vocabulary size. So m equal to k t to the power b. So k and b we already know they are the typical value parameters. K will be the value ranges from 30 to 100, but the fit according to the fittest value, the fittest value is 44. So we are using 44 here, and for b we are using 0.49 here. Okay. So after calculating this values by substituting the values in the formula, we got approximate value of 38,323. So the vocabulary size is 38,323. These are all unique terms. Okay, unique terms, that means not repeated. Every individual terms are different. They are unique terms. So Hibb's law suggests that the dictionary size continues to increase with more documents in the collection. So Hibb's law, we have two suggestions. The first one tells about the dictionary size, which increases when there are more documents in the collection. And the second second suggestion is that the size of the dictionary is quite large for larger collection. This is obvious, right? So when you have large number of collections, then automatically the size of the dictionary will be large. That's why we need a compression technique. So dictionary compression is important for an effective information retrieval system. That's why we need to perform the compression technique. So another law is Gibbs law. So first one is Gibbs law. So Gibbs law estimates the vocabulary size, and the second law is Gibbs law. So Gibbs law is to understand how we model the distribution of terms. So Gibbs law is to understand how we model the distribution of terms. So here you can see the statement for Gibbs law. It states that if T1, so T1 when you consider as term 1 in the collection, which means the most common term, the most common term in the collection. Okay, suppose when you write a document, normally particular term, all the individual terms you can prioritize according to their frequency. Okay, frequency means nothing but the number of times it occurs in the collection. So the most common term when you consider as the term 1, and the next most common term when you consider as the term 2, then the collection frequency. Collection frequency is denoted by CF of I of the ith most common term is proportional to 1 by I. So, this one. Suresh Chauhan, roll number 60. Okay, so it states that if T1, term 1 is the most common term in the collection, T2 is the next most common term, and so on. If T3 next third most common term, T4 next fourth most common term, and so on, then the collection frequency CF I of the ith most common term is proportional to 1 by I. Is proportional to 1 by I. So that is the rank frequency distribution is an inverse relation. So collection frequency is inversely proportional to 1 by I. Okay. So rank frequency distribution is an inverse relation. So the frequency of any word is inversely proportional to its rank. Rank is nothing but the number of this one, no? We will be assigning some rank, right? Say for example, if the, the For example, let me write here, if the occurs 200 times in a document and uh, next you can just give is occurs 100 times in a collection and suppose another one water, for example. Okay, this is the third one occurs uh, 30 times in a document. Okay, so if the occurs 200 times in a document, place occurs 100 times, and water occurs 30 times in the collection, for example. So how will you prioritize this based on the frequency? So if the is occurring 200 times, rank of rank of the will be 1. Okay. Then for place, rank of place will be 2. And where is it? Okay, okay. And for rank of water will be 3. Clear? So rank of water will be 3, like this. So when you have more number of frequency, then your rank will be less. Okay. More number of frequency, rank will be less. So that is what it is said here. The frequency of any word is inversely proportional to its rank. Inversely proportional to its rank. So you can see here the number. You have 200 number of does in the collection. Rank is 1. So it is inversely proportional because when you have more number of frequency, then lesser the rank. Okay. Then, so if the most frequent term occurs collection frequency this number of times, then the second most will be occurring half number of times, and the third most 1 by third, fourth most 1 by fourth, fifth most 1 by fifth, like this it goes on. Okay. So now we will see the example so that you will understand what is the Gibbs law. You just need to remember this statement here. Okay, collection frequency is inversely proportional to your this rank. Okay, what C collection frequency proportional 1 by I. So this statement you have to remember, and this statement you have to remember. Okay. So now we will see the example to understand Gibbs law. For example, if there are 1 million words, suppose the same example which I have given you, the is the most frequently occurring word, and by itself it accounts for nearly 1.7% of all occurring words. This is the second place of all history one. Oh, this one just an explanation of giving the ranking. Okay. So rank 1, the is rank 1. It occurs 69971 times. So this values are nothing but it is from a book. This book is Thomas Ritter's book or something. From that book, which is available online, they are just giving this example. So according to that book, the number of frequencies for the terms are listed out here. For example, the it occurs 69,971 times according to that book. Okay, this one is just for an example. Okay, all the values given here are based on the example book Thomas Peters, that example book. Okay, so with that, from referring the book, for the rank is 1, it occurs this number of times, and of is rank 2, this occurs 36,411 times, and the end rank is 3, this occurs 28852 number of times. The same example which I have given now. The occurs 200 times, then which the other word place occurs 100 times, water occurs 30 times, like that. Okay. So from according referring to the book, we have listed out the rank for three terms: the, of, and and. So number of third most frequent term will be number of most frequent term divided by 3. So this is how we got the number of third most frequent term. And number of second most frequent term, it will be number of most frequent term divided by 2. So these are all approximate values. You won't be getting the exact value. You can just check here. The most frequent term here is 69,971. So if I want to find out the third most uh, term, that is 28,225. So how will we get 28,225? It is 69,971 divided by 3. So this will give a value 28,852, which may be exactly the same value you may get, or otherwise in and around 28,000 you will get. Okay, so this is how we calculate the third most frequent term. Third most frequent term is calculated with this number of most frequent term divided by 3, and number of second most frequent term, it is most frequent term divided by 2. Most frequent term is this one. If it is divided by 2, we will get around 36,411, in and around 36,000. So this is how we find the second most frequent term. So if we know the first most frequent term, all other values can be calculated. Okay. So this is Gibbs law. So we have another statement for Gibbs law. We have another statement for Gibbs law. Let R be the rank of word, probability of R be the probability of a word at rank R. By definition, probability of R equals to frequency of R divided by N. So this is another statement for Gibbs law. So rank of, let R be the rank of the word, probability of R be the probability of a word at rank R. By definition, probability of R is equal to frequency of R divided by N. So where frequency of R is the number of times the word at rank R appears in the collection, and N is the total number of words in the collection, not number of unique words. This is not the number of unique words. N means the whole collection. So the whole total number of words. We are not counting the number of unique words. Unique words means say appears, rank, at, word. These are unique words. Suppose if da is also counted, this da is also counted, and another da, this is also counted, then this is the whole number of, total number of words in the collection. Okay. Then by Gibbs law, R into probability of R will give you a constant, which is similar to 0.1. A, R into probability of R, which is equal to A. A, in most cases, we got 0.1. A is nothing but a constant value. Okay. So I am giving you this example. You can solve it and you can get all the results by tomorrow. Okay. So now suppose if you have n equal to 3,73,100. Suppose n equal to 37,300, sorry, 3,73,100. And now we are going to find out all the probabilities, and also we will be finding out. So these two formulas we will be finding out. This one and also this one. Okay. Now first for the rank 1. So rank 1, Based on this data given here, rank 1 is the, which is 224,20,778 number of times. So this n we have written here using this formula, frequency of R. Then divided by 33,73,100, which is n. So this n. Okay. Now in 200 for probability percentage we are finding. So this is the value we get. Then finally R into PR. R into PR for the second statement. R into PR is this one. So the result you got here will be approximately similar to 0.1. So I'm getting 0.06488. So this is similar to 0.1 and equal to A. So similar to 0.1, then this is a constant, which is our constant value. So this one, okay. So give me 1 second. Hello. Hin. Naya, ikuto ko sa. So now, for the remaining ones, already the result is written here, but you need to solve in this way. You need to solve in this way, and the value you got here will be similar to this value. Okay, and you have to show me like this: probability of rank 1 in percentage. So you'll get a value like this, and again rank into probability of that particular term will be equal to similar to a constant A. So this first, this value is for the first word, first term, the, and for rank 2 also like this. For rank 3 until rank 11 you need to solve, and you need to solve for me. Okay. So I'll just share this one, and you can show me, solve it and show me the answer by tomorrow. The dictionary compression we will do tomorrow, because we have only 5 minutes, and dictionary compression we cannot complete today. So we will do dictionary compression by tomorrow. So what we have done today, index compression, lossless Hipps law, and Gibbs law. Index compression, types of compression, Hipps law, and Gibbs law. Who is present? Roll number 50. Right, is present.
Yes, ma'am.
Roll number 50. I already called you many times. You haven't responded when I call you.
Network problem, ma'am.
Your roll number is 50, right?
Yes, ma'am.
Okay. Anybody who's yet to give your attendance, you can inform me. And that's all for today. Others who have given your attendance, you can leave.